All right, let's dive right in. Today, we are talking about the secret weapons that engineers use to create the incredible high-performance metals that are literally all around us. We're talking about aluminum phase diagrams, and you're going to see why they're pretty much the GPS for inventing brand new alloys. So let's just start with the most basic question, right? How do you actually invent a new, stronger metal? I mean, if your job is to make a lighter airplane or a faster car, where do you even begin? Do you just, I don't know, throw a bunch of elements into a furnace and hope for the best?
Okay, let's make this totally real. Imagine a junior engineer on your team comes up to you and says, "Hey, I've got an idea. I think if we add both magnesium times and silicon to our aluminum, we can make it way, way stronger." Now, that sounds interesting, but how do you know? How can you be sure it's a brilliant idea and not a dead end that's going to cost a ton of time and money? Well, the answer, it's in the map.
This is how we get away from all that expensive guesswork and get into real predictive science. We use a tool called a phase diagram. And you should really think of it less like a paper map and more like a high-tech GPS that guides engineers through the super complex world of metals. So, what is it? At its heart, a phase diagram is just a map. It's a graph that tells you exactly what state or what phase a material is going to be in based on two really important things, temperature and its chemical makeup. You know, is it a liquid? Is it a solid? Is it some weird mix of different solid structures? The map tells all. Okay, check this out. Here's a really basic one, just for aluminum and silicon. That vertical line on the left, the y-axis, that's temperature. Hotter at the top, colder at the bottom. And the line across the bottom, the x-axis, shows how much silicon we're adding to the aluminum. All those lines and regions on the map, they're like borders between different states of being for the metal.
Now, that map reveals something absolutely crucial, and it's a little easier to see in this simple table. Look at this. At a high temperature, 577 degrees Celsius, you can dissolve a good bit of silicon, 1.65%, into solid aluminum. But look what happens when you cool it down to room temperature. That number just plummets to almost nothing, 0.008%.
The easiest way to think about this is like hot coffee. When the coffee's hot, you can dissolve a ton of sugar in it, right? In our case, that sugar is silicon. But as that coffee cools down, its ability to hold all that sugar just disappears. And that massive drop in solubility, well, that's the secret sauce. That's the thermodynamic key that lets us do some incredible things. So, we're going to use this principle of changing solubility to perform a little bit of metallurgical magic. It's called precipitation hardening. We're basically going to cook strength into the metal by forcing all those extra atoms, the ones that can no longer stay dissolved, to pop out and form brand new, super strong structures inside the aluminum.
And this magic actually follows a pretty clear four-step recipe. First, we do a solution treatment. We heat the alloy way up to dissolve all those extra elements, creating what's called a supersaturated solid solution. Then, step 2, we quench it. We cool it down incredibly fast, which traps all those atoms right where they are. Third, we age it. We gently reheat it just enough to let those trapped atoms start to move around and form tiny new structures called precipitates. And finally, the payoff. Those little precipitates act like microscopic roadblocks, making it way harder for the atomic layers to slide past each other, which makes the metal unbelievably strong.
And you know, this isn't some chaotic, random process. It's actually a very precise sequence of events happening inside the metal. It starts with just little clusters of atoms getting together, and then those grow and organize themselves into more complex structures before finally becoming distinct, stable phases. It's a carefully controlled evolution, all happening at the atomic level. And here it is. This is what it actually looks like. This is a micrograph image from inside one of these aluminum alloys. All those tiny needle-like things you see, those are the precipitates we just made. You are literally looking at the source of this alloy's strength. Every single one of them is one of those tiny roadblocks, making the material tougher. Okay, so now we get the recipe for making an alloy stronger. Let's circle all the way back to our junior engineer and her big idea. Remember, she wanted to add both silicon and magnesium. So it's time to pull out a more advanced map and see if her intuition was on the money. So what happens when you go from 2 ingredients to 3? Well, your simple line graph turns into a triangle. This is called a ternary diagram. Each corner of the triangle represents 100% of an element, so aluminum, silicon, and magnesium. Any point inside that triangle is some specific mix of all 3. Our engineer's idea lives somewhere on this map. And now we zoom in. This is a detailed slice of that AMMG psi map at a specific temperature. Each of these little zones with these kind of cryptic labels tells you the exact combination of phases that will exist at that composition. The answer to our engineer's question is hiding in plain sight, right here on this chart.
But before we find it on the map, the research already gives us a huge clue. This quote from our source material says that when you add magnesium to an aluminum silicon alloy, it loves to form a specific compound called magnesium silicide, or Mg2Si, and this compound is known to be fantastic for enhancing strength and hardness. And boom, there it is. Look at the map. This whole region right here, the one labeled alpha plus beta Mg2Si, that's it. The map is predicting that in this zone, you'll form exactly the powerful strengthening compound we were just talking about, magnesium silicide. The map told us what would happen before we even lit the furnace. The engineer's idea, it was brilliant.
So the GPS worked. It guided us right to the destination, a successful new alloy. But this is so much bigger than just this one example. Phase diagrams are, and I mean this, the fundamental language of modern materials design. Just look at this. On the left, you see a phase diagram for an alloy with 5 different elements. It looks incredibly complicated, right? But because engineers can create and, more importantly, read these maps, they can produce the real-world high-performance alloy you see on the right. There's a direct, unbreakable line connecting that theoretical map to physical reality. So what's the big takeaway from all this? Why does it matter? Because these maps let us avoid incredibly expensive trial and error. They give us the power to precisely design new materials with the exact properties we want. They are the scientific foundation for just about every single advanced metal alloy we use today, from the phone in your pocket to the jets in the sky.
And that leaves us with a really fascinating thought to end on. Today, scientists are designing things called high-entropy alloys, with 5, 6, 7, even more elements all mixed together. As we keep pushing those boundaries, trying to create materials that are stronger, lighter, and tougher than ever before, you just have to wonder, what will the impossibly complex maps of the future even look like? And what new wonders will they help us discover?